Okay, so today we will talk about section 5.6. Section 5.6. And it's called the Gray-Schmidt organization process. It's the last topic in this chapter. Gray-Schmidt organization process. Gray-Schmidt organization process. It's famous result. And let's recall some. Actually, for this one, when we talk about, it's the last topic in chapter 5. It's in chapter 5, and in the beginning of this chapter 5.1. When we talk about chapter 5.1, we have already said some result in this part. Just some special case, yeah. Okay, so let me tell you the relationship for this section and section 1 and section 1. So let's recall. First of all, let's recall. If we have two vectors in our, if we have two vectors in Rn or in R2, that's fine, yeah. And originally we have and these two vectors are orthogonal. If they are orthogonal, then what can we say? Orthogonal, two vectors are orthogonal in xy plane. What does it mean? In xy plane, we know that it means that it's our x1, it's our x2. I mean, the angle must be 90 degrees, right? Because we have this formula cosine theta equals, in denominator is the product of the length. Numerator is the inner product. So orthogonal means that the inner product equals 0. So once you plug in the value 0, you will get it's 0. So theta is 90 degrees. So if two vectors are orthogonal, means that the angle between these two vectors is 90 degrees. And we know that if two vectors are orthogonal, in section 5.1, we have said that they must be linearly independent. Set. They must be linearly independent set in R2 space. And linearly independent is an important concept. In chapter 4, we know when we talk about chapter 3, when we talk about vector space, a basis in R space, a basis in a vector space. It's an important concept. And what does a basis mean? It means that it's a space set and it's linearly independent. Okay, so linearly independent set is an important concept. And what's the relationship between linearly independent set and orthogonal set? It's this one. Orthogonal set must be linearly independent set. But for the converse, we don't have. If two vectors are linearly independent, it doesn't mean that they are orthogonal. Actually, we know that if they are orthogonal, actually two vectors we always have this one, right? So if they are orthogonal, means that cosine theta equals 0, means that the angle must be 90 degrees. But as we know, we could consider two vectors. For example, it's 1, 1. Our vector, and the second vector is this one. It's 1, 0. These two vectors, they are linearly independent. It means that one is not a multiple of another one. Yeah, this vector is not a multiple of this one. This vector is not a multiple of this one. So they are linearly independent. But the angle is 45 degrees. It's not 90 degrees. So they are orthogonal. If you check their inner product, it's not equals 0. If you check the inner product, it's not equals 0. Okay, so linearly independent set is not orthogonal set. So now what we want to consider, actually in section 5.1, we have said that if we have two linearly independent sets, although they are not orthogonal, but we should construct two vectors such that they are orthogonal. and they have the same spanning set. Okay, I mean, of course, now it's in R2 space. When we consider its spanning set and two vectors their spanning set, it should be equal to R2 space. But even in Rn space, it's true. It's true. I mean, now, okay, it's second step. We have two vectors, S1, S2, belong to R2. Now, we know that they are linearly independent. And we want to find two vectors u1, u2 such that we want to find such that they are orthogonal. And their span says span x1, x2 equals span u1, u2. I mean, for the span set, even in Rn space, it's true. Even in the Rn space, S1 and S2, they are vectors in Rn space, and they are linearly independent. And now we want to find u1, u2, two vectors in Rn space. They are orthogonal, and they have the same spanning set. The reason why we consider Rn space is that we want to consider general case. I mean, later we will consider R3 and R3 and the general case Rn. Then we should use this result. We should use the similar result. So now we should expand this part. Of course, I will tell you the general formula, but if you understand the process, it will better for you to memorize this result. Yeah. So now let's see. We want to find u1, u2. We want to find u1, u2 such that u1, u2 are also orthogonal set, and they have the same spanning set as x1, s2, And how to solve it? How to find it? If you remember that in section 5.1, how to find it? We have a plane in xy. So now a plane. We have xy plane. In xy plane, you could start from x1 or you could start from s2. If we start from s1, and now we have a vector s2. How to find two vectors which are orthogonal? For the vector s2, we could consider its projection, right? P1 projection. P1 is the vector projection. Projection of x2 onto s1. Because now we fix s1, so it's a projection onto s1. Yeah. So now, and we know that P1 its formula is P1 equals x2 s1. We project onto s1, so we consider s1 we divide by its length. And P1 has the same direction as s1, so we multiply by s1, but we should divide by its length. So our P1 formula is this one, the projection P1 is this one. And as a graph, you could see that now we consider S2 subject P1. So the vector S2 subject P1 is orthogonal to x1. So x1 and S2 subject P1, they are orthogonal, right? So indeed, we know that here we have this one. S1, S2 subject P1, They are orthogonal. Okay, they are orthogonal. And now, but our goal is to find orthonormal. So, and now we have two vectors which are also orthogonal. How to get two orthonormal? How to get orthonormal set? Just divide it by its length, right? Just divide by its length. So now we divide by its length. And divide by its length, now it becomes orthonormal set. in R2. Even in Rn it's the same. It becomes also normal set. But now I want to explain this part. They have the same spacing. And of course in R2 space, if it's in R2 space, of course, both of these two spaces is x1 is this one, x2 is this one, their space is R2. And here for this vector, sorry, I have one result need to mention. Okay, so here I should mention something. Yeah, so here I want to explain this one, but before that, I forgot to mention the notation. Here, P1 is exactly this one. S2, S1 sub divided by S1, S1 divided by S1 is length. And here, for these two vectors, we denote by U1, we denote by U2. Because later we will use the same notation, similar same notation. So here is our U1. Here is our U1. And here also normal. Yeah. Okay, this one. So S1, S2 linear independent, S1, S2 subtract P1, where P1 is this vector, they are orthogonal, and we divide by its length, they are also normal. And we denote by, first vector we denote by U1, second vector we denote by U2. Okay, denoted by U2. Okay, and then now we want to expand this one. S1, S2 their spanning set equals U1, U2 their spanning set equals U1, U2 their spanning set. And as we said, if just in this case, R2 space, if just in this case R2 space, then S1, S2, their spanning set is R2. And the U1, U2, S2 subtract P1 is this one. Even you just divide by its length, it's still of the direction. And the S1 divided by its length is still of the direction. So their space also equals R2. So of course it's true. But now even in Rn space, it's also true. Even for the vectors x1, x2 in Rn space, they still have this result. They have the same space, and we should explain this one. Since later we will consider general case, x1, x2 belong to R3 or Rn, and we just have two vectors, then it's still true. Okay, so now let's see they have the same space. But so you should compare with these two vectors. These two sets. Here is our S1. S1 is x1, x2, and S2. S2 is U1, U2. And then when you consider the spanning set, first vector x1, first vector U1. U1 is just divided by its length. For the vector S1, we just divide by its length. So they have the same spanning set, x1 and U1, they have the same spanning set. So now we consider S2 and U2, and then consider S2 and U2. So here, just tell you how to show it. Of course, you could just, for the, it's a little, for this part, you could, of course you could skip it, but for this part, I just explain it, and if you understand, you will better to let you understand this part. Yeah, you will be better. Anyway, so here, now let's see, here we have a vector x2. The first one, we know that x2 subtract p, we start from which one? S2 subtract S2 divide U1. What's this? Here, this one is exactly this one. We denote by this one. P1 is S2 U1. The inner product has U1. So this part is P1, right? So it's S2 subtract P1. This 10 is S2 subtract P1. This one. And S2 subtract P1, what's this? It's the numerator of the vector U2. So we could multiply by its length in both sides. So it's S2 subtract P1. its length times U2 times U2. So what do we have? What do we have? If you move this 10 to right hand side, you will get S2 equals S2 subtract P1, its length times U2. It's the first 10, and the second 10 plus S2 U1 is inner product times U1. This one, right? So S2 equals some scalar times U2 plus some scalar times U1. So it belongs to U1, U2 layer spacing. U1, U2 layer spacing. So X2 belong to U1, U2 layer spacing. U1, U2 layer spacing. And the second step, now we should consider U2. Now consider U2. But U2 is definition is this one. So U2 is definition in this one. It's a quotient. So we separate. I mean, it's 1 over its denominator, S2 subtract P1, multiplied by S2 subtract P1. This one. But and the S2 subtract P1 this vector we put it down. So it's 1 over S2 subtract P1. P1 is length. Its length. Times S2 subtract P1 is S2 S1 divided by its length multiplied by S1 divided by its length divided by its length. This one. Okay. And then now when you do the distribution, it's just the distribution. Here it's a constant times S2. And this part is a constant times x1 divided by a constant. Right? So it's still x1 is a multiple. And the first term is a multiple of x1, S2. So first term is multiple of S2, second term is multiple of S1. So both of them belong to S1, S2 layer spacing. So it belongs to S1, S2 layer spacing. Okay. So now we know that X2 belongs to U1, U2 layer spacing. U2 belongs to X1, S2 layer spacing. So indeed, we know that span X1, X2 equals span U1, U2 equals span U1, U2 equals U1, U2. Even they X1, S2 in Rn space. Now we could find U1, U2 two orthogonal vectors whose spacing equals spacing of X1, S2. Spacing of U1, U2 equals spacing of X1, S2. Okay. And the concept is important. The concept is important since even in R3 space we will use similar way to explain it. Okay. Yeah, so now I will tell you the three-dimensional case and tell you the general result, and finally give you two examples, then we finish it. Yeah, and I think this section is a little complicated, but of course you should remember the formulas. Here it's just two vectors, and it's just the formula in section 5.1. But at least you should know. I mean we will think about more second test. Second three-dimensional case. Now we consider three-dimensional case and tell you how to derive the formula. Okay. Okay. So are you ready? Okay, so now let's consider the case in R3 space, S1, S2, S3. in R3 space. And we have three vectors, S1, S2, S3. They are linear independent. And we want to construct three vectors which are orthogonal or orthonormal, such that their spanning set equals S1, S2, S3, their spanning set. So what we want to do is to construct, even in N space it's the same. We want to find U1, U2, U3 such that they are U1, U2, U3 they are orthonormal or orthogonal, or you could say orthonormal. Actually, we want to find orthonormal. But orthonormal just divided by its length is enough. And their spanning set S1, S2, S3 equals their spanning set U1, U2, U3. It's our goal. And we still use similar way in previous result. Yeah. Okay. And now we have three vectors. They are linearly independent. We know that they are not orthonormal. Okay. So how to figure out these three vectors? And for convenience, of course we should fix some vector and consider. And for another one, we should construct new vector. For another one and the last one. Yeah. And now we fix S1. So for convenience, we just let S1 be in the x-axis and then let S2 be in the xy plane. Yeah, just for convenience, without lose of generality, we could just think about this simple case. Yeah, so here is here we should graph it. We have the graph. In three-dimensional case, just in three-dimensional case, x, y, z. In three-dimensional case, it should be x, y, z. Also, okay, so now, yeah, so I should correct it. I mean, for the x1, we consider the vector in y-axis. For x1, it's in y-axis. X1 is in y-axis. And x2 we consider x1 in y-axis, x2 in xy plane. It's xy plane. And of course, x3 is another vector. Yeah, so x1 is the vector in. x1 is just the vector. It's our x1 in y-axis. In other words, x1 is its coordinate. It's 0. Some scalar 0. It's a reform. Y-axis, just in y-axis. So x equals 0, g equals 0. And x2 in xy plane. So x2 I denote by it's in xy plane. So probably it's this one. It's our S2. So in xy plane, so it's star g equals 0. It's a reform. G equals 0 in xy plane. And S3, of course, S3 in R3 space. So S3 probably is this one. General case. This one, it's our S3. Okay, so just simple case, and actually for convenience or without lose of generality, we could let S1 be y-axis, let S2 be in xy plane, and S3 be general vector. Yeah. And for these three vectors, how to find? Of course, for here there is one thing I want to mention that for these three vectors, x1, x2 they could span xy plane, and the x3 is not in xy plane. So the span set of x1, x2, x3 is R3 space. Okay. Okay, but okay. So now how to get the u1, u2, u3? If we have s1, s2, then we could use the previous result, right? So we use the previous result. I mean, remember that? What's our previous result? S2, S1, we have a vector S2. Originally we have vector S1. How to get orthogonal vectors? Consider its vector projection, right? It's our vector projection. And consider S2 subtract P1, right? S2 subtract P1. We consider S1, S2 subtract P1. But originally we consider this one, S2 subtract P1. But it's not, it's orthogonal, not orthonormal. So finally we should divide by its length. Right? Okay, so again, here, similar, we consider the P1, the projection. P1, here is our P1. And here for this vector is what we want to consider. The vector is what we want to consider. S2 subtract P1. This one. So we start from the vector x1. So here I tell you each step. First step, for the vector, we fix s1. So we start from the vector s1. So for this vector s1, if it's R2 space, for the vector s1, we should divide by its length to get u1, right? It's our u1, it's our u2. So in R3 space, for the vector S1, we should divide by its length. So it's our first step. And the second step, for the vector x2, what can we do? For the vector s2, what can we do? If in R2 space, for the vector x2, we should consider vector projection and then consider their subtraction and divide by its length. Use the similar argument. We should consider similar argument. How to get the P1? We should consider the projection P1 firstly. So S2, and here for this one we denote by U1. Okay. So for this vector we denote by U1. And here we denote by U1. U1 is just divided by its length. And we denote by U1. And here we consider the inner product. S2 U1 their inner product. Multiplied by U1. U1 is this guy. So vector projection. First of all, we consider the vector projection. Is the projection of x2 onto s1. And once we have vector projection P2, we consider S2 subtract P1. So after that, we consider S2 subtract P1. The third step, we consider S2 subtract P1. S2 subtract P1, but we should divide by its length. So third step is consider S2 subtract P1, but also divide by its length. And it's what we want, U2. So U2 vector, which property do we have? Their span set. We know that span set of x1, x2 equals span set of u1, u2. Even as we say, even in R3 space, Rn space, this property also holds. Okay, so in R3 space, first step, for the vector s1, we should divide by its length. Second step, for the x2, S1, we should consider vector projection of S2 onto S1. And S2 subtract P1 divided by its length is our U2. And the next. Now, span x1, s2 in this example. Span x1, s2 is the xy plane. In this example, span x1, s2 and the span u1, u2 is just the R2 SY plane. It's just the SY plane. In this example, simple example, it's just the SY plane. So now we have another vector S3, vector S3, and we have a plane. And what's the vector? Now for the vector S3, how to construct another vector U3? How to construct it? Similar argument. Here we have vector S1 and then S2. We consider the vector projection S2 onto S1, right? And now we have a plane. The plane is spanned by x1, s2, and the vector s3. We still consider the projection x3, the projection of s3 onto s1, s2 layer spanning set, onto s1, s2 layer spanning set. So here, the third step, the next step, for the vector x3, what can we do? What can we do? We consider projection of S3 onto S1, S2. So it's a little more complicated. I mean, actually we consider the P2. Similar one, but firstly, we should write down the P2. If I explain by the graph, it means that we consider the vector projection is our P3. And this part is actually S3 subject P3. S3 subject P3. But it's not univector, so we should divide by its length. But now, what's the projection P3? The projection P3 is the projection of S3 onto S1, S2, onto span of S1, S2. So what's the projection? So the next step is this one. We should consider P2. In the P2 is a projection of S3 onto S1, S2 the spanning set. But onto spanning set of S1, S2 equals spanning set of U1, U2, right? So if you remember here remember that for the projection of S2 onto S1, we have this form. For the projection of S2 onto S1, we have this form. So now for the projection of S3 onto S1, S2, we have similar form. I mean, here for this case, we just have the vector U1. So it's a spanning set of, it belongs to the spanning set of U1, right? And now P2, it belongs to spanning set of X1, S2. In other words, it belongs to the spanning set of U1, U2. So we have 3 times. X3, U1 inner product times U1. But issue is belong to U1, U2 their spanning set. So we still have another 10. S3, U2 times U2. Should be this one. And this part we call it projection of S3 onto U1, U2, onto span of S1, S2, onto span S1, S2, onto span S1, S2. But span S1, S2 equals span U1, U2, equals span U1, U2. They have similar form. So in this formula P2, we should use the vector S3 and the vector U1 and the vector U2, So in this step, it's our first step, second step, third step, and then the fourth step. So in this fourth step, you should use this one, and you also need to use U1. You should use the vector S3 and the vector U1 and the vector U2 to get the projection of S3 onto their spanning set. And once you have this 10, our final step is this one. It's our final step. Just let U3 be final step. We let U3 be this one. Just let U3 be S3 subtract P3, right? S3 subtract P3. But we should we should have we need the unit vector, so we should divide by its unit vector. Divide by its unit vector. And here, as you see, this vector S3 subtract P3, this vector, it will be orthogonal to any vector in xy plane, right? It will be orthogonal to any vector in xy plane. In other words, this vector S3 subtract P3, it will be orthogonal to U1, since U1 is a multiple of S1, and U2, since U2 belong to xy plane, since U2 belong to xy plane, since U2 belong to xy plane. So, yeah. So here, for this one. And for this one, it also have this part. I mean, with span U1, U2, U3 equals span S1, S2, S3. S1, S2, S3. And here I should mention that for this one, we know that U1, U2, now U1, U2, in this part, U1, U2, they are orthogonal, so they are also normal set. They are orthogonal and they are also unit vectors. So in this step, we know that U1, U2, they are also normal set. In this step, since S2 subtract P1 is orthogonal to S1, and in this step, we know that U1, U2, U3, they are also normal set. They are also normal set. Okay, they are also normal set. Yeah, and the process we call it Gram-Schmidt process. So finally, what's our solution U1, U2, U3? Our solution U1, U2, U3 is this one. Is exactly this one. U1 is S1 divided by its length. U2 is S2 subtract vector projection of S2 onto S1, but we should divide by its length. S3 is subtract P2. P2 is the vector projection of S3 onto x1, S2, onto S1, S2, and its definition is this one. But we should divide by its length. And they are also normal set. In R3. But in R3, its dimension is 3, and we have 3 vectors. So of course, they are also normal bases. In this case, of course, they are also normal bases. Yeah. So I think it's the argument. And now the last one is I write down the general theory, and later I will give you the example. Later I will give you 2 examples to practice. Okay. So I erase it and give you the theory. First step, second step, third step. I mean, we have 5 steps to figure out length. We have 5 steps, and it's important. We have 5 steps. It's our S1 and S3. It's S3, and we have S2. Yeah, and it's our S1. So the process is important. Since I want to write down the theory, so I keep this part. Okay, so the theory is called Gram-Schmidt. It's famous result, Gram-Schmidt process. And it says that we have n vectors. It's a basis of Rn. And how to get the orthonormal basis? Just let U1, as we say, I just erase it. Anyway, U1 is this one, U2 is this one, U3 is this one. Okay, so let U1 be S1 divided by its length. And so on. Okay, U2 I could write more 10. S2. And general is UK plus 1 is xk plus 1 subtract pk. Oh, sorry, here is S2 subtract P2. P1, sorry, P1. And xk plus 1 subtract pk divided by its length. And what's the projection pk? What's the projection pk? It's defined by this way, where pk equals pk, the vector pk, it belong to span cell, of x1, x2 until sk subtract 1. Here, p1, k, sk, p1 belong to span cell of u1, and it also means that it belong to span cell of x1. p2 belong to span cell of x1, s2. So and it's defined by this way. So similarly, we define it by a similar way. Here, for S3, for P2, we can see S3, U1 their inner product, S3, U2 their inner product. So PK we consider the vector SK plus 1. We consider the SK plus 1. But first term we consider U1 as U1. Second term we consider U2 as U2 until U. The last term is UK, right? UK as UK. It's divided by this way. And this vector is a projection. It's a projection of xk plus 1 onto which one? Span cell of U1, U2 until UK. It also means span cell of x1, s2 until sk. So onto span cell of s1. Oh, it's our result. Span cell U1, U2, UK. If we define U1 by this way, U2 by this way, UK plus 1 by this way, and here PK means this one. And the PK is the projection of SK plus 1 onto the span cell of U1, the span cell from U1 to UK. Then what's our result? Our result is that as we show in the case R2 equals 2. R equals 2. We know that then first one, the span cell, as we say, the span cell from S1 to SK is equal to span cell from U1 to UK. From U1 to UK. First one. And the second one, I mean they have the same span cell. Second one, U1, U2. Oh, here I forgot to mention it. K is greater than 1 and less than n subtract 1. So it contains all the. So here U1, U2 until UN. So indeed, here we have U1, U2 until UN. And it's also normal basis. Also no basis of Rn. It's also no basis of Rn. And then the process we call it Gram-Schmidt process. It's famous result. Okay. Yeah. So later I will give you the examples. We will practice two examples. Okay.